Suppose that there is a particle of charge Q immersed in a sodium chloride solution. If Q is positive, the particle will attract chlorine ions and repel sodium ions. If Q is negative, the particle will attract sodium ions and repel chlorine ions. The presence of the ions will alter the electrostatic potential of the particle. We would like to derive an equation for the electrostatic potential as a function of distance from the particle that takes into account the effects of the ions. We first need to derive a mathematical expression for the concentration of sodium and chlorine as a function of distance from the particle. By definition, the number density N of R of sodium or chlorine ions at a distance r is the number of ions in a spherical shell of radius r and thickness dr divided by the volume of the shell. The number of ions in the shell is the total number of ions times the probability that the given ion will be in the shell. The volume of the shell is 4 pi r squared dr. The probability of finding a given ion in the shell can be found as follows. If the ion is at distance r from the particle, it will have an energy E. Thus, the ion is equivalent to a system with many energy levels, one for every possible distance r. Statistical mechanics tells us that if we have a system with a set of energy levels, the probability density of being in an energy level with energy E is the number of states with energy E, G of E, times Boltzmann's factor, E to the negative E over kT, divided by the partition function Z of the ion. The partition function is simply the integral of G of E times the Boltzmann's factor over all the energy levels. Since all positions at distance r have the same energy, the number of states with energy E must be proportional to the number of positions in space at distance r, which must be proportional to the area of a sphere of radius r. Thus, G of E must be proportional to 4 pi r squared, and since G of E occurs in both the numerator and the denominator, whatever the proportionality constant is between the number of points in space and the area must cancel. We can write the total number of ions as the average concentration in naught times the volume, and we can write the volume as the integral of 1 over all space. The integrals cancel because they both go to infinity at the same rate. This is because we assume the energy of an ion is 0 at infinity, so the exponential is 1, and the two integrals are the same. The 4 pi r squared dr cancels. The result is that the concentration of ions is the average concentration times the Boltzmann factor. Now let's derive the electrostatic potential of the charged particle in this ionic solution. First, write Poisson's equations, which tells us that the Laplacian of the potential is proportional to the charge density. The proportionality constant is negative 1 over the dielectric constant epsilon times the permittivity of free space epsilon naught. The charge density is the charge density of sodium plus the charge density of chlorine. The charge density of sodium is just the charge of a sodium ion E times the number of sodium ions per unit volume N+, and the charge density of chlorine is just the charge of a chlorine ion negative E times the number of chlorine ions per unit volume N-. E is the proton charge. Factor out the proton charge. We've already computed the concentration of an ion as a function of position. Replace N+ and N- with the previously derived expression. Note that we are assuming that both ions have the same average concentration N0. E+ is the energy of a sodium ion at distance r, and E- is the energy of a chlorine ion at distance r. Factor out an N0. Distribute a negative sign. The energy of a particle is its charge times the electrostatic potential phi at distance r. Multiply and divide by 2. Use the definition of hyperbolic sign. This is the nonlinear Poisson-Boltzmann equation. It must be solved numerically for the electrostatic potential. If we make some approximations, we can get an analytic solution. First, write the nonlinear Poisson-Boltzmann equation with the exponentials, not with the hyperbolic sign. Then, assume that the electrostatic energy is much less than kT. The exponents of the exponentials is then very small so that we can expand the exponentials to first order. Since we are assuming spherical symmetry, write the Laplacian in spherical coordinates, setting all theta and phi derivatives equal to 0. Multiply both sides by r squared. Use the product rule on the left-hand side. Define 2 N0 E squared over epsilon naught kT as 1 over the debye length squared, where lambda sub d denotes the debye length. Plug this equation into Mathematica to get the solution. We need to impose constraints to get the arbitrary constants, C1 and C2. We demand that the potential vanishes at infinity, so C2 equals 0. We want to recover Coulomb's law when no ions are present, so we demand that in the limit of infinite debye length, the potential is Q over 4 pi epsilon epsilon naught. This requires that C1 equals Q over 4 pi epsilon epsilon naught. Thus, the potential of a particle of charge Q immersed in an ionic solution is Coulomb's law attenuated by an exponential factor.